The goal of this video is to solve problems involving projectile motion by breaking the motion down into vertical and horizontal components. This is Peter. When Peter throws a projectile, it will follow a parabolic path. Tracing the parabolic path of Peter's projectile, we can consider a few snapshots of the ball along the path. The velocity of the ball at any given moment will be tangential to the path the ball takes. To measure the motion of the ball, we need to choose a coordinate axis. Let's pick the initial position of the ball to be our origin and define the positive x and y directions to match the initial motion of the ball. Rightward is positive x and upward is positive y. If we assume that there is no air resistance and that this all occurs on Earth, then we can confidently say that as soon as the ball leaves Peter's hand, there is no acceleration in the horizontal direction and a constant acceleration due to gravity in the vertical direction. The acceleration due to gravity will be the same everywhere along the ball's path, so we can easily sketch in this acceleration everywhere. The velocity vectors, then, can be broken down into their horizontal and vertical components. When working with vectors, always work with perpendicular components separately. We can mathematically determine what the velocity in the x and y directions are by taking the antiderivative of the accelerations. The horizontal velocity will be constant everywhere, since there is no horizontal acceleration. This will be equal to the initial horizontal velocity given to the ball, and also to v sub 2, since the velocity has only a horizontal component there. The vertical velocity will vary with time according to the acceleration due to gravity times time, plus our initial vertical velocity. We can do this once more to determine what the horizontal and vertical positions must be as functions of time. The horizontal position, x, will be our initial x velocity times time, plus whatever position we started at, x0. And the vertical position, y, will be 1/2 times the acceleration due to gravity times time squared, plus our initial velocity in the y direction times time, plus our initial y position. This is the equation for a parabolic line. Notice also the symmetry of the problem at hand. Our initial position and the fifth position are at the same height from the top of the curve, where the vertical velocity is equal to 0. On the left side of the screen, the ball has started with some velocity v0y, which decreased to 0. Then, on the right side, the speed in the vertical direction started from 0 and increased over the same distance. As a result, the vertical velocity at this fifth position must be equal in magnitude to the initial velocity, although opposite in direction. The same argument can be made for any 2 points on the curve that have the same height. Assuming the acceleration due to gravity to be about 10 meters per second downward, let's pick an initial velocity and see if we can determine how long it will take for the ball to return to the same height it was thrown from. Because there is no time dependence of the velocity in the x direction, we can only consider the velocity in the y direction. The change in velocity in the y direction is simply the acceleration due to gravity times time. But to use this direction, I need to know the velocity I'm ending with. Recognize that the vertical velocity is 0 at the top of the curve, and solve for the time interval of just the ascension. Recognizing that in the absence of air resistance, it takes just as long for the ball to rise as it does to fall, we can simply double this time to get the answer we're looking for. Alternatively, I can recognize that the vertical velocity at any 2 positions of equal height must be equal in magnitude. So plugging in these numbers immediately returns the time interval in question. Plotting the position, velocity, and acceleration versus time can be done quickly for each dimension separately. The vertical acceleration is a horizontal line at a equals -10 meters per second, whereas the horizontal acceleration is a horizontal line at 0 meters per second. The vertical velocity is then a line with a constant slope of -10, starting from our initial y velocity. Notice that the magnitude of the y velocity is reflected across the point where it crosses the x-axis at 1.5 seconds. And the horizontal velocity is a horizontal line at our initial x velocity. The vertical position has a familiar parabolic shape, which reaches a maximum value at 1.5 seconds and returns to its original height at t equals 3 seconds, then continues to fall below Peter's hand and to the ground. The horizontal position, on the other hand, simply continues to increase at a steady rate equal to the initial horizontal velocity. Let's consider another example. Peter is taken to the high seas and become a pirate. He knows his ship well enough to know how high above the water his cannons are and how fast they fire cannonballs. The question, then, is how close he has to get to another ship to hit it. Start by defining a coordinate axis for this problem. We can place the origin anywhere we want, but to make it easy on ourselves, let's again place the origin where our cannonball started, and define the positive x and y directions to match what we already know the motion of the ball to be like. Let's make rightward positive x and downward positive y. This way, both h and d will have positive values. Again, we consider the vertical and horizontal components separately. In the absence of air resistance, the moment the cannonball leaves the cannon, there will be no horizontal acceleration. Therefore, the horizontal velocity must be constant, equal to our initial velocity since the ball is fired horizontally. Then, the horizontal position is just v0 times t plus our initial position. In the vertical direction, we have a constant acceleration due to gravity, and so we solve for our vertical position as a function of time the way as we've done already. However, since in this case, our initial vertical velocity is 0, we're really only dealing with the second half of the parabola, and we can drop those terms from our equations. The horizontal distance then is just our displacement x of t minus x0, so d is equal to v0 t. To get t out of the equation, we need to look back at the vertical direction. The vertical distance h is equal to y of t minus y0, so h is equal to 1/2 times the acceleration due to gravity times t squared. This time, then, is the time it'll take for the cannonball to hit the water, so I can plug it into my equation for d to get an answer in terms of exclusively known variables. So to fire the cannonball further, they need to either be shot faster or the cannons need to be built higher. And remember, Peter the Pirate's projectile paths are parabolic.